Hello and welcome back to Tensor Analysis, the new video series where we talk about vectors, multilinear maps, and how we can combine them to so-called tensors. In fact, the goal of this video series is to demystify the concept of a tensor from a mathematical point of view. You might already know that these so-called tensors occur a lot in applications, especially in physics, and without a mathematical foundation, they can be a little bit confusing. However, before I tell you about the outline of the course, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And you should know, as a member on Steady or Patreon, you can just download the additional material for all the videos by clicking the link in the description. And now, without further ado, let's immediately put this new course into my network of topics. And here I can already tell you, as a prerequisite, you will definitely need my basic linear algebra course. Moreover, also at least the beginning of my more advanced linear algebra course will be needed here. The reason for that is simply that we will need the abstract concept of a vector space here. And then later on, we will also combine some analysis topics, so you need some knowledge of my multivariable calculus course. So please keep that in mind. In order to enjoy this new course here, you should definitely already have some good knowledge about linear algebra and analysis. And the reason for that is that in the end of tensor analysis, I want to build a bridge to my more advanced course about manifolds. Indeed, the whole power of tensors only becomes apparent when we study them on manifolds. However, before we can even do this step, we first have to understand all the linear algebra parts in tensor analysis. This is something we could call multilinear algebra because we will study so-called multilinear maps. And by having these nice maps on vector spaces, we can already define the so-called tensor product of vector spaces. So you could say we get a new object there where the elements are just called tensors. And at this point I will also tell you about the common names one uses in this context, which is contravariant and covariant. And then afterwards we can also talk a lot about applications, and then finally we should talk about tensor fields on manifolds. In fact, a really famous application of tensor fields on manifolds is given in general relativity in physics. However, there and in other applications, it's always a conflict if you want to calculate in coordinates or on an abstract level. Therefore, I would say to see the strength of tensor analysis is to look at both sides at the same time. So on the one hand, we have a concrete level, and on the other hand, we have an abstract level. And the concrete level here means that we have coordinates that are always given with respect to a basis. And you should already know that for the simple case of an n-dimensional vector space, where any vector v can be represented by n coordinates. This works whenever we fix a basis in our vector space v, and then the given vector is just a column vector. So for a real vector space, the column vector would live in Rn. And the coordinates we will denote by x1, x2, and so on. And here you might recognize that I use a superscript instead of a subscript to denote the number of the coordinate. This is something you should already remember for tensor analysis. The position of the index will carry an additional piece of information. But of course I will explain this concept in more detail in the next videos. First we should look at another abstract concept you might already know, namely a linear map L between two vector spaces. And then by choosing a basis on V and a basis on W, we can represent L by a matrix. This means the matrix with its components is on the concrete level. And there we also have indices to denote the columns and rows. This means in contrast to before, now we actually have two indices involved. And at this point I can already tell you, the general concept of a tensor will just be to go to an arbitrary number of indices. So let's say we have an abstract map phi on the right hand side, then we have components of phi on the concrete level. And in fact, to enumerate them, we will always use lowercase Greek letters. So here we have mu1, mu2, and so on, and moreover we can also have subscripts and superscripts. In fact, here on the abstract level, we have a so-called multilinear map phi. This means it can have many vectors from V as inputs and a vector from W as an output. So in this case here, we would have n factors in the Cartesian product on the left. And now you already see, instead of calculating with this abstract multilinear map, you could just calculate with the components as we do it with a matrix for a linear map. And at this point I can already tell you that in general we will have a lot of subscripts and a lot of superscripts involved. And this will also be a representation of a multilinear map. However, now this multilinear map phi will also get inputs from the dual space of V. The dual space V star is not so complicated and something we will discuss soon. But this already explains how we can distinguish subscripts and superscripts. The multilinear map can just have different inputs from V star and V. And now in order to keep it a little bit simpler, we just map phi into the real number line R. So at this point I've already told you a lot. You see the rough concept of a tensor here without knowing the explicit definition. In fact, all the things on the left hand side and all the things on the right hand side are just known as tensors. So this is already good to know. If someone calls an object with a lot of indices a tensor, then you know it represents a special multilinear map. How this relation actually works in practice we will see soon, but you already see that linear algebra is involved. And now I want to finish this introduction by giving an explicit example. And this one you might already know, it's an epsilon symbol and called the Levi-Civita symbol. And in fact it has 3 indices, so in our context we will call it the Levi-Civita tensor. And there the 3 subscripts, mu1, mu2 and mu3 should only cover 1, 2 and 3. And now the definition of epsilon is quite simple, because we just have to look at the 6 possible permutations of this set. If we have an even permutation, the value should be 1, and if we have an odd permutation, the value should be -1. And all other combinations should just give 0. This means we just have to look in which order the 3 indices occur. For example, you can see it like that. If we count upwards in a cyclic manner, then we have an even permutation, and if we count the other way around, we have an odd permutation. For example, 2, 1, 3 is an odd permutation because we can count 3, 2, 1. So now you see, something we call a tensor does not have to be complicated at all. However, already with this simple example, you should see that the standard visualization as we have it for matrices breaks down. A matrix we can put into a rectangular form because we only have 2 indices. There, as you know, the first index counts the rows and the second index counts the columns. But now with 3 indices, we actually have to go to the 3rd dimension as well. So you already see that this is not feasible at all as a visualization for a general tensor. So for an object with a lot of indices, it does not make sense to write it down like that. However, maybe let's still do it for the Levi-Civita tensor here by looking at 3 layers. This means for the first layer here, the last index is given by 1. And this immediately implies that we get out 0 if one of the other 2 indices is 1 as well. So the first row and the first column here have to be 0. Moreover, the diagonal also has to be 0 because there the other 2 indices coincide. So only these 2 entries are non-zero, and for that one we see we have 2, 3, 1. So we count upwards, so we have a 1. And in the other one we count 3, 2, 1, so we have -1. And now in order to take the numbers into the second layer, let's take it out. So there the 3rd index is always given by 2. And this tells us we have zeros in the 2nd row and also in the 2nd column. And then as before, we also have it in the diagonal, and then only these 2 positions remain. And counting 3, 1, 2 gives us a +1 here and a -1 there. And then finally we can go to the 3rd layer, which is also not more complicated. In fact, there we also already know where all the zeros have to be, and then we can check the 2 remaining positions. And you immediately see there we have +1 and here -1. Okay, now by seeing this whole picture here, you could say that a tensor is a higher dimensional matrix or a generalization of this concept. And this is already a good rough idea, but the precise mathematical definition should come in the next videos. Therefore, I really hope I meet you there again, and I wish you a nice day. Bye bye.